Bismillahirrahmanirrahim. Assalamu alaikum dear viewers, I am Dr. Noshin Afshan and you are watching Dr. Noshin Afshan YouTube. I hope that all of you would be fine and I am thankful to you for watching this video. To watch more videos, please subscribe my channel and press bell icon. Our today's lecture is about structure of alkanes according to hybridization concept, in which we will discuss structure of specific examples of alkanes, that are methane and ethane. But first of all, we will see that what is hybridization. So now let's begin. So talking about the hybridization, it is the process of intermixing of atomic orbitals of the similar energy level to form the hybrid orbitals of the similar shape and comparable energy levels. For example, 2s orbital intermixes with 2px orbital. So both of these orbitals belong to the second shell and are at almost similar energy level, and these would intermix to form hybrid orbitals, and these hybrid orbital would be s and p. When you will write down the hybrid orbital, then you will mix these two orbitals and write them collectively as a one word. So these would be hybrid orbital and represented as sp, and that would be sp hybrid orbital. And as these are 1 and 2, so here two atomic orbitals intermix to form two hybrid orbitals, one that are hybrid orbital sp and hybrid orbital sp. So these would be identical in shape as well as in energy level. The hybrid orbitals are denoted like this. Here there is a larger lobe and accompanied with the smaller lobe. So in this way, these are lobe shaped, and these two hybrid orbitals are at similar energy level. So now we apply the concept of hybridization, that is in fact an extension of valence bond theory, that is VBT, to the structure of methane. So in methane, as you know, that this is the CH4, where one carbon is attached with 4 hydrogen atoms, and the geometry of this methane molecule is tetrahedral in shape. So we will discuss that how the methane molecule is said to have the tetrahedral geometry. So we start from the electronic configuration of this carbon atom that is attached with the 4 other hydrogens. As you know that the electronic configuration of carbon is shown like this. Here the atomic number of carbon is 6, this one, and here the 1s orbital is filled with 2 electrons, then 2 electrons are in 2s orbital, then 2px with 1 electron, 2py has 1 electron, and 2pz is empty. But this state or this condition is at its ground state. But when this carbon atom absorbs some energy, and as a result the one electron from this 2s orbital absorbs the energy and it jumps from this 2s orbital to this 2pz orbital, and as a result the condition becomes like this. Here 1s filled with 2 electrons or completely filled, then 2s orbital becomes partially filled because 1 electron has been jumped to the 2pz orbital. When these orbitals are filled with 1 electron only, then they are also called as partially filled, but in the case they are filled with 2 electrons, then they are called as completely filled. So the 2px has 1 electron, 2py with 1 electron, and 2pz has also 1 electron, and this condition is at its excited state. So at its excited state, 1s has 2 electrons, 2s1, 2px1, 2py1 and 2pz1. So here, when these atomic orbitals would intermix to form the hybrid orbitals, then 1s orbital would not be will not take part in the hybridization process or in the intermixing, because we already have said that the intermixing of atomic orbitals of the similar energy level, that is here 2 from the second shell, these are also from the second shell, so these 4 atomic orbitals are almost at the similar energy level, so these would intermix to form the hybrid orbitals that are sp3, because here 1s orbital and 3 p orbitals, px, 2px, 2py and 2pz, so there are total 3 number of p orbitals that are taking part in the process of intermixing. So here it is denoted as sp3 hybrid orbitals. Now the point is, how many hybrid orbitals have been formed? Only 1 or 4? This shows that 3 p orbitals have taken part in the process of intermixing, but there are actually 4 sp3 hybrid orbitals, and that 4 figure would be written the left hand side of this sp3, because this would indicate that okay, when they would intermix, then 1, 2, 3 and 4, total 4 hybrid orbitals would be formed. These figures would show that how many orbitals have been formed. S1, so only one s orbital has been taken part, and this notation shows that there are 3 p orbitals have taken part, and this figure would show that how many hybrid orbitals have been formed. These numbers would represent the number of atomic orbitals, and this would show the number of hybrid orbitals. So there are total 4 sp3 hybrid orbitals have been formed. And if we see their orientation, then it looks like this. Here, that is 2s orbital. Okay. Here it is the 2px, then 2py and 2pz. So these would intermix to form 4 hybrid orbitals, and every hybrid orbital would have this shape. This lobe would be very much smaller as compared to this lobe. So in this way there would be 4 hybrid orbitals, and this is sp3 hybrid orbital. So the next point comes that how these sp3 hybrid orbitals would align themselves to form the CH4 compound. As there are 4 sp3 hybrid orbitals, so they would align themselves in such a way that one orbital would come over here, the second orbital, the third one and the fourth one. So these are not exactly same like this, rather it is little bit in this way. It is tilted to an angle, like here there are 3. Here it is not exactly at this position, rather it is slightly bent, because it would show the 3 corners of the tetrahedron. So this is sp3 These are the sp3 hybrid orbitals. And now the 4 hydrogen atoms would also combine with these hybrid orbitals. As you know that the electronic configuration of hydrogen is like this 1s1, because hydrogen has only one atomic number, and so its 1s orbital is partially filled. If we denote the electrons in these hybrid orbitals, then every hybrid orbitals would have one electron as according to the electrons in the atomic orbitals, because in the atomic orbitals s and 3p orbitals would have had only one electron, so the hybrid orbitals would also have one electron in each of them. So now this 1s orbital of the hydrogen, that is like this, it would share its electron with these hybrid orbital like this. So the second electron that would be filled in this shared region would have the opposite spin, not the same spin. This is the 1s orbital of hydrogen. Similarly, here it would also have the one electron in addition to the other one electron, and that one electron would be from 1s orbital of hydrogen. And similar case would happen with each of these hybrid orbitals. So in this way, here there is one more point with respect to their orientation, like orientation of the hybrid orbitals, why they align themselves in a tetrahedron geometry. Because if they are aligned in this way, okay, means the bond angle between them is, if we divide the 80° in 4 equal halves, then it would be 20°. Okay, if the angle between two bond pairs is just 20°, here 20°, and here 20°. So if the bond angle is only 20°, then there would be maximum repulsion between them, and these would not be stabilized. So in this way, for the sake of stabilization of these electrons in the hybrid orbitals, they would orient themselves at far apart from one and each other. So if the bond angle would be like, for example, 20°, then they would not be stabilized. So for the sake of stabilization of these hybrid orbitals, they would be as far apart as possible from one another. So here in the tetrahedron shape, the bond angle is 109°, and this 109° is like HCH bond angle, comes out to be 109°, and this bond angle shows its geometry as tetrahedron. Geometry is tetrahedron. So first of all, we measure its bond angle, and then we apply this value of the bond angle to its geometry, and this 109° between every HCH, if you measure the bond angle between this hydrogen, carbon and hydrogen, the bond angle would be 109. If you measure the bond angle between these hydrogens, carbon and hydrogen, the bond angle would be same, 109. If you measure the bond angle between this hydrogen, carbon and hydrogen, that is this, the bond angle is still 109 degree. And similarly, between these HCH, the bond angle is also 109 degree. So this 109 degree bond angle applies to every HCH bond, and that shows the hybrid orbitals are oriented in the tetrahedron geometry, and same would be after their combining with the hydrogen 1s orbital. So in this way, we have started from the electronic configuration of the carbon atom to the intermixing to form 4 sp3 hybrid orbitals, and then their alignment in the tetrahedron geometry, then their combination with the 1s orbital of the hydrogen, and then we have seen that they take up a geometry like this in the simplified version, and then the bond angle becomes 109 degree and the geometry is tetrahedral in shape. So both of these geometries are almost similar. This is with respect to hybrid orbital, but this one is the simplified version of the methane molecule. So we will end with the geometry of this methane molecule as the tetrahedron. Now the structure of methane according to the hybridization concept comes to an end. So thank you very much for watching the video. Please subscribe my channel and press bell icon, and also let me know in the comment section that how much do you like this video. So, Allah Hafiz.